I'm happy to introduce today Jonas Ashley, who is doing his PhD studies in University of Zurich. Jonas is working in hydrogen physics and specialized in computing and data analysis. And today Jonas will tell about high performance computing in Python, and especially using the TensorFlow package. And tomorrow he'll talk in details about the Z-fit, so the Python library for fitting. So Jonas, please start. Yeah, once I want to say that we will record this workshop and probably distribute the record to some other students or make it public. So please keep it in mind. Okay, thank you.
Okay, thank you very much for the introduction and for the invitation to be here. Yeah, I think this is mostly already said. I'm mostly doing fitting, and this just requires fast computation. Doing that in Python, this is sometimes a little bit trickier. So this workshop is to give you an idea of what high performance computing looks like in Python. We have a little overview here of what is going to be in these 2 days. I will first talk about high performance computing itself, and then more specific in Python, going over to then the TensorFlow library and having a tutorial in the end. And today 2 is more on statistical inference, specifically on the Python tool Z-fit that is based on top of TensorFlow, also with a more extensive tutorial then. So maybe to make clear what this is not just a talk about TensorFlow, the technical details, as I, let's say, assume you're, let's say, scientists, you know a little bit of Python, you maybe have heard or used NumPy a little bit, but you're not technical experts in something, so it's not a high level entry for TensorFlow, but this really is to give a certain understanding of why we're doing that, should we use TensorFlow or not, in which cases, and what are actually the problems that we're trying to solve here. Because high performance computing is a problem with many facets. So on one hand, we have physical components and structures, we have different software layers. And what I noticed is that if we don't have a full understanding on that, I often get questions like the one below, like, well, why don't we run everything on a GPU? Why is it not using all of my CPUs? Why is Python slow and all these things? So this is why the beginning, let's say the first half of the whole talk, will mainly be about what is high performance computing, how do computers work, why are there bottlenecks, why basically answer all these questions and more, so that you also understand then why certain things work or why they don't. So we'll start out with the hardware of a computer works. Maybe some of you know that, I think roughly already. We won't go into many details. This is sometimes also oversimplified. It's just to give an idea of the essential components to everyone and what crucial role they play and what problems we can solve by certain principles. So just to give you an idea of where we've come is, first computers are quite a long time ago, 50s, 60s, and they were rather big. We had a frequency of like 5 kilohertz. This on the right actually is the miasm, which is the Malé Elektrony Счетная Машина. So the first Russian computer actually. And today we're at a few nanometers of transistor sizes and frequencies of gigahertz, so a million higher. While some of the things changed dramatically, other things did not so much change, and they're crucial to know. One essential part is that the most used architecture for computers today is still the so-called von Neumann architecture. This, on the right side below, is basically a schematic view of how a computer works. We do have in the middle a CPU, which is a central processing unit, which is the CPU as we all know it. Actually, it is a little bit split up. There's a control unit that looks where to put stuff. There are registers for instructions, and there's the arithmetic logical unit, which actually does the computation. But more crucially, we need to get in somehow the data and the program into our processing unit. And this is done through the memory, or let's say in general input-output. And the problem is that this means for every calculation that we do, we first need to gather the stuff from memory, move it to the CPU, do our calculation, move it back to memory. And this is quite a lot of bottleneck. This is also called the phenomenon bottleneck because everything, the code that we're executing and all the data always has to go through this memory. And this is very slow compared to how fast the CPU actually can do calculations. Now, there are some approaches to mitigate this problem. One of them is caches. So instead of having just the CPU and the memory, what we have in between are so-called caches, which are smaller memories, way smaller memories. So as you see below in the order of kilobytes or megabytes, that store the, let's say, often accessed data or code. So if we do a computation and we need the array again in the next step, we can just move it to the level 1 cache and then keep it there, then access it again, which is way faster. The problem with that is, of course, it's a little bit tricky to know what is going to be used next. Well, often this depends on the computation before, and in general, if you run an operating system, it's just not easy to do that. Another thing is that we can do branch prediction. Sometimes the CPU runs even stuff in parallel already that it guesses that can be run, which means we already fetch from the memory stuff that we think we might need, and maybe we don't need it, and then we just throw it away. And another thing is also virtual cores. This, I think, is a concept that you also heard. If you look at the machines, they're sometimes quad cores, but what you see are actually 8 CPUs, not 4. And the reason is that there are, let's say, 4 physical CPUs in there, but because the CPU is so fast compared to that I/O bottleneck, that it's often worth to basically just split between 2 tasks. So you have one CPU that does the computation, but it first does something for task 1. When it's finished, it moves that to the memory and gets the next one. But until the next one arrives, it does something for the task 2. Then it finishes task 2 and does that to the memory request from the new memory. And in between, the task 1 from the memory is arrived. So this is what virtual cores are, which also imposes a simple limitation of those, meaning that if the limiting factor is not moving stuff back and forth from the memory, then a virtual core is not really useful. Let's say if we need to just, if we have everything basically on a CPU all the time and working with that, as we often do in high performance computing, then sometimes more core are actually not useful. So if you have a quad core, sometimes using 8 cores instead of 4 cores doesn't really give you a speed up because this I/O is not really the bottleneck. When we say CPU, this is actually a general purpose CPU, and they run with machine code. Machine code is basically a set of instructions that have stuff like to jump to a certain point, to load a certain data set, to add, and so on. This is very specific, though, to a CPU, and this is an important part because we'll see later on, there's always this trade-off between generality and something specific. Also, these instructions, they are usually not optimized. They're very general. They're made to add one number, they're made to add, to do this and this operation, they made to take a square root, but they always have something like, okay, go to that memory, load this into it, go to that memory, load this into it, now add the 2, and I get it out again. And one crucial optimization to make high performance computing, to make computing faster per se, is to have more specific instructions. So that we say, okay, this loading and stuff, we actually can do that smarter. If you know, for example, we want to add up 100 numbers, then we can already preload the next number because we already know that this is going to be used. Or we can even parallelize it or something like that. So one crucial way to speed up things is to build better, more specific instructions. We will also see that later on, that they're even coming up to our high level because we're here now when a very low level, but all this stuff come through at some point. And what we can also use is specialized hardware. Instead of having this multi-purpose, general purpose CPU, we can have stuff like GPUs, as you surely know, FPGAs, just accelerators in general, TPUs and whatever. The disadvantage is that the data transfer from a CPU to such a specialized device is quite slow. On the other hand, the specialized device is fully specialized on doing a certain type of computation, as we'll see for the GPU later on, and can provide crucial speed up. And this is already the first thing of this generality versus specialization. So we can have a more general CPU, which is very nice and can do a lot of stuff, but not so fast, or we can have hardware that is very specialized in certain things, or instructions that are very specialized and can provide a huge speed up, but they're specialized, they're not general. So in high performance computing, we're always on this trade-off, and we try to basically merge that. So something else that you maybe know is the clock rate. That's just how fast the CPU works, and this is often used as the speed, but this is not the only improvement in speed. It's one of those, but this instructions improvements, the cache and all this stuff, this is, I would say, as important, nearly as important as the clock rate. But the clock rate is, in general, the main thing to speed up a CPU, is mostly historically. And this is basically, it says when to do something. So in the CPU, everything goes a certain step. There is this frequency. And one of the things is if you build smaller transistor, then everything can just move faster around. I mean, technically, we're having electrons moving around in the CPU and the transistors. The shorter the distance, the faster the electrons reach their target, meaning we can have a faster clock cycle. There is, though, one huge problem which we started hitting, let's say, in the beginning of the 2000s, 2005 something, which is the so-called power wall. Namely, that the energy dissipation of a CPU is roughly proportional to power law, frequency to the power of 3 or something. What this means is there is something which you may have heard, Moore's law or something. It's usually a little bit abused. It's not exactly, this is more in transistor size. That's why it's in quotation marks, but it basically says that the CPU, let's say the CPU power doubles every like 1.5 years or something. So it's exponentially increasing the CPU power. So it's not directly about frequency. There is other laws which basically tell that, but so far it was basically just increasing the frequency. The problem is we can't do this anymore because of the power dissipation. If we just double the frequency, we're gonna have a cubic increase in the power consumption. This is just not feasible anymore. As you can see on this plot, we see that the number of transistors still increase. We see that the frequency saturates together with the single thread performance. So meaning a single thread, a single CPU is not really increasing anymore. It's still like this because, as I said, frequency is not the only thing to improve speed. These instructions and stuff also improve speed, but basically this is saturating. We also see that the power is saturating. And what we see rising, on the other hand, is the number of logical cores. You can see from 2005 when this is just increasing. And this is basically what today is mainly driving the increase in performance of computing. So currently we're in the age of parallelization, and parallelization itself is just like a new topic. So what does this mean if we now want to go parallel instead of just executing things like we've done so far? By the way, one thing I did not mention, in case you have any kind of questions, you're free also just to ask here. If I'm going too fast on anything, you can just tell me. Or if you feel like you didn't understand something, we're not so many, so just feel free to ask in the voice chat. So multiprocessors today, computer doesn't have a single core anymore, but it looks rather like the picture on the right, that we have, for example, 2 CPUs, and then we have these caches, and we have some shared cache, and we have main memory, and so on. Some of the memory, as we see, can be shared, some is not. And to now parallelize a task, we can just simply think, we will go into more detail later on, it means we can either have, the best thing is if we make on a very high level the cut. So if you have, for example, 2 scripts that we want to run, we want to process 2 data files, and we have 2 scripts for that, then run 1 script on CPU 1 and 1 script on CPU 2, and they're working perfectly independent. That's the easiest way to go. What we can also do is trying to parallelize our code on a lower level. So really making an addition of 2 arrays, parallelizing that. But this can get very tricky because then we need to move, let's say, half of the array of array 1 to the first CPU and the other half of array 2 also to the first CPU, but then the other half of array 1 and the other half of array 2 to CPU 2. So they're now split up. Then we add them and then we move them back again, which means we need to actively split. We have a lot of moving out and in. We don't know actually what is going to be afterwards. Maybe if we sum off all the array afterwards, it's even more efficient to just run it on one CPU because we don't need to move it back and forth. Maybe we also don't need it anymore, so we can split it up. So it's not clear what we're going to do afterwards with it. And this is very tricky now to schedule how we really want to parallelize that. I mean, on a high level, it's very simple because it doesn't really matter on the time if you have a script that runs for seconds or minutes. But if you have a computation that runs for nanoseconds, then moving them from the L3 cache, let's say, to CPU1 and then to CPU2, because now the value is needed with the other values from the CPU2, this is very costly. So it's a non-trivial problem. One important thing there, though, is called the vectorization. As I mentioned before, there can be different instructions. And one of these is called SIMD, which is single instruction, multiple data, meaning that if you get in a lot of data and you need to apply the same operation on this data, this can be done very efficiently because the CPU already knows, okay, we're going to have like 100,000 floats and all I need to do is always divide them by 2. So this can be done in a very efficient manner. And the GPU is very good at doing that. What you see in this picture is on the left is the CPU, and we have all these cores, and we have each core can act independently completely. And what we see on the right is a GPU, and every green tile is basically a core itself, but they're not independent. So they're like in blocks, basically. And all they can do is apply the same operation simultaneously, but to a lot of data. Meaning if you have a vector of like 1,000 events, we can just do a square root of it and put it through to the GPU. While on the CPU, this will take way longer because it has to just 4 cores. On the other hand, we cannot apply a different operation to every element on the GPU. That's very inefficient. On the CPU, we can all do that. Again, CPU more specialized, GPU way more specific. And basically contains these SIMD units. So we've seen now a GPU, we've seen multi-CPU. In fact, reality is even more difficult because we can even have clusters, meaning different nodes, computing nodes connected. And this is a certain illustration of how it looks in reality. So we have a CPU which has, let's say, a few cores, and these cores share some memory, but then we have different CPUs with not shared memory. So they have really to communicate through a line in the cluster, and we also have the GPU. And now the big one, and I think it's clear that, as I mentioned, the bottleneck, so I/O is always very, very expensive, meaning moving something from one CPU to the other CPU because it's needed there is expensive. Moving one from one node to the other node is very expensive, insanely expensive. Let's say this can take milliseconds even, I mean, worst case or something, or let's say microseconds, but the computation takes nanoseconds, and the GPU as well. So the question now that we can ask ourselves is, imagine we have 3 arrays and we want to add them. I mean, what do we do? Should we, so we have array A and B and C. Should we move them to the GPU, which takes some time, but it's very efficiently there? Should we split them among nodes? Maybe split array 1 and 2 and 3 all like in 4 equal parts? Should we do, I mean, if you have just 10 entries, it's clearly not worth it. But if you have like 10 million entries, I guess it's worth it again. And this is absolutely not clear here. So what we see here, and the main conclusion from all that is that the real world layout is pretty complex. Also, I mean, we didn't take into consideration now even the caches that are more and less efficient, right? So we want to keep things also close to a CPU, and some are bigger, some are smaller. So if you want to do this efficiently, on one hand, okay, it's quite a pain to do it. But secondly, what we also know is if you want to use this infrastructure as efficient as possible, it means that we would need to know as much of the computation beforehand. Because one of the main things is if I add 2 vectors, then before you want to, if you want to distribute now, you need to task add these 2 vectors. One thing is surely you want to know, okay, how many entries? maybe 10 entries not worth, 10 million entries it's worth to split it up. And second is, what do you want to do afterwards with the tensors? If you don't need them anymore, or do you anyway need to split them and do something else? Do you want to add a third array because then I already take the third array there, or I can split things up? So knowing what will happen afterwards, knowing the whole computation beforehand is what we actually want, because then we can really schedule. If we don't know that, we're very much lost, and in every step we lose so much time moving things back and forth. So this is basically the main problem from an architecture point of view. To use the architecture efficiently, we need to be very static, know as much as possible beforehand and not be dynamic. Now, we looked at how this parallelism look like on a hardware side. And while this already looks a little bit complicated, we can now have a look at what it means in software. If you now really want to implement a parallelization, because again, we're in the age of parallelization, we need this parallelization basically for high performance computing. And what I'm having here is not real Python code, it's a little bit pseudocode to just give you an idea. And what you can do as a very simple thing is we can just have the shared memory, let's say, meaning we could just have multiple CPUs or threads. Let's assume now 2 threads here that just run exactly the same code. And what you see in the upper script, all we have is an array, and both CPUs can see this array. We start out with E equals 0s, and E is also shared between them. So now one thread goes into the while, which says, okay, when I is smaller than the length of the shared array, then assign shared array at the ith position number 42, and then increase I by 1. And you know, now I is 1, and actually the next thread goes in there as well, so I is 1, while and then checks that, and the other thread already starts in the beginning again. So they can both just solve the same problem, right? It's just increasing the I. Or we can also do the thing below, which is basically the same. But one problem here is so-called race conditions. As we see, so if we run this code, what we will get is an out of bounds error. So index out of bounds. It will tell you, I mean, I is 200. You can't, there is no 200th element in the shared array. And if you already had experience with parallel or let's say asynchronous maybe computing, then this maybe sounds trivial to you. If you didn't have that, then look very precisely at the code. Because from our understanding so far, this can't really be. I mean, how can it be that at line 4, it says an out of bounds error I is 200, if you say that only, let's say the shared array has 200 elements in there. If the shared array, I mean, if it's smaller than the shared array, go in there. If it's equal to the shared array, then don't go into the while. So we having here now a problem. We cannot protect ourselves anymore from this kind of things. What really happens is basically you see in the second box is that while, so you see like thread 1 is on line 3 and it enters and I is 199. Then thread 2 is also on line 3, I is 199 perfectly well, this enters. Now thread 1 is on line 4 and increases the I. Now thread 2 is also on line 4 and also increases the I. Now thread 1 is on line 5 and now it's 201, which we can't have. So this is a race condition. We can't now say, if you put something like, if E equals smaller than 200, do this and this. Now we don't know whether E is really smaller than 200. If you code serial, E will be always smaller than 200. But now we can't say this anymore, because maybe between the if E equals smaller than 200 and other process already increased E. So you see, we're creating here problems that did not exist before. And there are ways, of course, to mitigate that. Parallel computing itself is a whole, let's say, scientific field, I would call it, which is something called locks. And a lock basically means, or exclusive access, there are many names for that. It's just to give you an idea of what you can do and what you can't do and what you should not do, or why you shouldn't do anything. And that is, you can basically say, okay, you know, what you see on the right is that lock I, meaning basically if I is now locked, so now only I can access I, which means if there any other thread wants to have I as well, they have to wait now at the line lock. So this runs perfectly well with one CPU. But if you have now several CPUs, what this means is two things. On one hand, we have one problem in this code to the right. The else does not release the lock. So as soon as one takes the I, locks the I, and then goes into the else, it won't release the lock anymore because it actually releases the lock in a thing, which is a bug in this code here, but it's intentionally. Meaning if the lock is not released, then all the other processes that are waiting at the lock I will wait forever until you kill your code, which is just something of how easy you can make a mistake. More importantly though, it's also not really efficient. So because most of your code, most of your threads will now just wait at the lock, and then one gets the lock, gets into that and releases it. But the main time of the computation, which is in between the locks. So anyway, just one thread is really doing something. So what I'm just demonstrating here is it's not that easy. You can even actually say that this is called deadlock. If you run this on one CPU even, and I mean, I'm not sure how much you can follow all these thoughts. If you're a little bit into it, it's fine. You can also look through it afterwards if you're interested to understand these problems. So it's just like, imagine you running just one CPU, you go inside, you lock it, then you're in the if, you release it again, and so on until there is an else, and it goes on with a while. And then later on, it wants to acquire the lock again. But it can't because it forgot to release it on the else. Meaning now the process itself is holding the lock, and it wants to get the lock again, and it can't. Meaning it has deadlocked itself and is waiting there forever. So you see, while we usually in serial code, which is pretty used in normal problems that we know how to debug them, here we get a whole new set of problems. We could raise conditions where we can have inefficiencies. And this is one of the takeaways of this distributed computing. In the code example that I showed before, this is the serial problem was already solved. I mean, this was an oversimplified problem, but usually if you code something, we already struggle to implement the right code just normally. I mean, if you write bug-free code and it runs, we're already very happy with that. Now it just added many complications with these locks for something that seems like a trivial problem. Let's just add the things in parallel. And what I wanted to compare this to is usually a serial code problem is a one-dimensional problem. So the example below says if E is larger than 0, then we know from now on E is larger than 0. Sounds trivial if you're in serial code, but in parallel code, we have a two-dimensional problem. We have other processes doing stuff as well. If you say E equals larger than 0, we don't know what it's going to be. Doesn't mean anything. We have to have a complete new set of things. But one of the main concepts is this kind of lock, which is also a word that often appears in high-performance computing, whatever library you're using, locking or exclusive access, which is to prevent kind of race conditions. That the value is not changed while one process is using it. Another thing to know, it's just basically about a little bit of vocabulary that you also understand, because some documentation also in TensorFlow uses this word, is inter-process communication. Before we had the same shared memory, and there is also a non-shared memory. If you think of nodes, if you think of different computers or something, meaning what we have now is one parallelization. For example, with MPI, we can do is we can have a script and run this on different processes, and every script that runs has then its own ID. What we then can do is we can calculate something depending on the own ID number, and we can add so-called send and receive nodes. A send and receive node meaning, as you see in line 4 or 5, it means, you know, send this value to the partner to the right, and receive the result from the partner to the left. Which, for example, if you do any kind of fluid dynamics simulation or something, it's very common thing to do. So you're actively putting in their send, and then this sends it over some kind of protocol. But we have to do this actively, which is nice because now it's a little more explicit. However, now we have to think of many things, like what is if your ID is the lowest or the highest? And if you look at this example, this is also a complete deadlock of itself, because now if everyone sends to the right and waits for them to receive, we're deadlocked because no one is receiving, everyone is waiting for the others to receive. So we have to now split some send, some receive, or all this kind of thing. So I'm just saying again here, even if you have more explicit, the send and receive nodes are quite a thing to know. It's just, it's a lot of complication again that we're inserting that is non-trivial to solve. So you can also think, one question is then also what to parallelize. Should we really parallelize on the level of an addition, or should we parallelize higher above? And I mean, the answer is parallelize as high as you can, because it's less pain to do. One thing that was not so explicitly mentioned, but becomes maybe obvious with the send and receives, is that we didn't just add complications, we also added a lot of computational overhead. As mentioned before, the send and receives, they are very slow because they're going over data communication somewhere. So maybe all we've done was slowing down our computation by a factor of 100 by trying to speed it up by doing it parallel. So it's absolutely not clear whether something is even worse to parallelize. And compared to other optimizations where you usually can't do a lot of harm, here you can do a whole lot of harm. It's not just faster because you parallelize. So these are somewhat the takeaways of the parallelism. Just words a lock usually. There are also different locks, re-entry locks, and so on, or tokens. There are exclusive access. We have send and receive nodes, that is communication between devices, or let's say between processes, between separated memories. And it can really slow down your code. It's very simple because we had a lot of overhead there. We're trying to be smarter, but it's a lot of overhead. And the main thing is it really adds another dimensionality of very hard to spot problems. So these are the hardest among them because sometimes you don't see them. Sometimes it's a race condition that just happen every 1000th time that you run your code. This is an absolute nightmare. It's fun to try once, but the takeaway that I would really give you is keep the hands away from doing serious manual low-level parallelization. It's quite a hard thing. Delegate it if you can somehow to any other library, which, just as a very small side note, for example, this is a link to an issue of TensorFlow where there are quite good computer software engineers that know this stuff very well. And this is a bug I've discovered, for example, which is a deadlock, classical deadlock. As before, it blocks itself from entering again. Even for those it happens, so better we keep away from it. So what I'm going to mention now is about what's actually the execution speed in terms of software. Something that we didn't really consider because we just look at the hardware and how to parallelize computation, but how fast is actually software computed. And this is something with compilation. I think this says something to most of you. Basically, there is two things. It's ahead of time compilation usually, which means we first compile it, then we execute it, as you may know from C++ or something. And there is another kind which is called just-in-time compilation, which we will look at more, and this is more relevant for us. But in general, compilation means we have a high-level representation of something, and we're going to have a specialized, optimized representation of something. This is basically the definition of compilation, be it ahead of time or be it just in time. Now, Python itself, the language, is an interpreted language. So it's needed. It's not AOT. It's not JIT. It's interpreted, meaning every line of code gets interpreted live. It's no in this sense compilation going on. It's no more specific implementation. It really goes through, reads every word, and executes this word, which is very dynamic, and that's great for usage. But it also means that it's quite slow because it can't make any optimizations because it doesn't do any kind of specialized representation. What we can do though is to make use of precompiled functions in other languages, so that have specialized implementation for certain things. if you look at, there are specialized libraries, for example, for math, which is NumPy array or a constant, what we have on the left is a pure Python list. And we can ask ourselves, okay, what's the difference now between the left and the right? And the answer here is that the list is just a special case of something way more general. A list can handle arbitrary objects. It can have dictionaries, it can have strings in there, it can have anything. So a list is absolutely not optimized and very, very general thing, while an array or a tensor, which say it's on this level the same, is a very well-defined object. So this says we have exactly 4 elements. We have it in the memory, it lies next to each other. It's all type, let's say, float 64. So it's a very specific representation of something. And as we've learned before, specific is fast because it means we can make assumptions. We can now, if we get an array of 100 floats, we can use optimized instructions. If you get a list of 100 objects, for every single object, we have to see how can we add these, what can we do with those, what are they actually, where in the memory are they? For an array, it's all clear, they're all stuck together. So one of the example is NumPy, as I think you know, and I think you all know as well this simple example of doing a for loop of adding things or doing a NumPy operation. And NumPy operation is so much faster because there are so many assumptions in the np.add, because the np.add knows basically all I'm going to process is 2 arrays. I know the exact type. They're all next to each other in the memories. They have exactly the same layout. So I can have very optimized instructions. While for Python, the for loop, anything can happen in there. So there's no way to look ahead, no statical stuff. Now, another thing, basically, instead of doing AOT compilation, is just-in-time compilation, which means we do, during runtime of a code, we produce more specific code, which is optimized. What this means is we call a certain function in Python, and we have certain inputs there. Now, this code is run, it's just normally executed. And now, basically, the runtime looks at what happens. For example, we want to add 2 numbers in Python. Now we could say, okay, now all the function does actually is it just adds 2 numbers. Well, we don't need to have a full Python function for that. We can have a very optimized implementation for that. So now let's remember that whenever we add these 2 numbers, we don't use this Python function anymore, but the optimized Python function that is very specific to just adding 2 numbers, and remember this. So now if this is called again with the same type, it just uses this remembered specialized implementation. And some languages implement this by default, like PyPy or Julia. And some provide as a functionality. One of the things is number. Maybe you've heard of that as well. If you do something in Python or also Python NumPy, it's a great library to do this kind of JIT, as you see on the lower right. What it means is literally you give in something, in this example, a matrix, and you can't even do for loops in number. And then it tries to infer the types, it goes through it and creates specialized machine code for exactly this function. I mean, of course, there are limits. I mean, because if you want to make something more specific, we intrinsically lose generality. So if you have a function that's very general stuff, we can't really gain a lot. But for things like this, which is really just a math operation, we can implement this way more efficient than using the whole dynamicity of Python. Meaning, so far, the summary of the whole HPC problem, why we're doing that, is we have a computer architecture that is fairly complex. We have I/O bottlenecks, we have caches. To circumvent that, we have specialized instructions such as SIMD, signal and input multiple data. We need to do parallelization, basically, because we can't increase the frequency anymore. And this adds another layer of complexity. Most importantly, though, we need to plan ahead because we don't have just one CPU where all the stuff is there. One way to plan ahead and improve this, make it more statically, is to do AOT compilation, which is very performance friendly if we specify all the types beforehand, but it's very user unfriendly. Python has a lot of dynamicity, and this is very comfortable for the user. So we can call this AOT library in Python, or we can also do JIT compilation, which just creates specific implementation for certain parts. However, the main thing is always statically versus dynamically doing something in high performance computing. The more static we are, the better. The more dynamic we are, the more user-friendly, but the worse. One thing that I didn't mention at all so far is, what do we actually optimize in the code? I mean, do we not need to optimize everything as dev? And this is just a general takeaway. Usually 2% of the code takes up 98% of the time. So don't care about the 98%, because even if you reduce the time of the 98% to 0, we just speed up the code by 2%. And the question is, of course, how do we find this 2% then? And the answer in the most cases is just we measure it by profiling. Meaning, this is what also good computer engineers will tell you, just profile it, because it's very hard to guess usually, due to this complexity of the structure, to guess what is really a bottleneck. Sometimes we can use like knowledge and experience, so we can guess, well, like if we add vectors, then let's use NumPy. It's just easier, it's also more visible and stuff, and it can be, I mean, if we do that for loops, it's a bottleneck. Okay, that we know for sure.